Welcome to this course on Theory of Plasticity for Engineers, Concepts and Applications. We are dealing with Module 5 where we are dealing with computational aspects of plasticity. In this lecture, we are going to look at incremental elastic plastic theory and understand the convex return mapping algorithms that is used for implementation of elastic plastic theory. Now, the outline of the lecture is as follows. First, we are going to deal with formulation of the initial boundary value problem. Then we are going to follow an energy framework, and then we are going to understand dissipation and well-posedness of the boundary value problem, and we are going to discuss the numerical solution approach that is going to be adopted, and we will discuss in detail return mapping algorithm that is used for isotropic hardening and for combined isotropic and kinematic hardening. So, first we have the initial boundary value problem, kinematics of that problem and description of the domain, discussing the case in a one-dimensional situation to understand the concepts better. So, we are discussing an one-dimensional problem and numerical implementation in one dimensions. So, B bar describes the domain, and dou B is the boundaries of the domain. T is belonging to closed interval 0 comma capital T, which is a total time step that also denotes the loading step. The displacement field is denoted by U. Now, the strain and velocity fields are given by the derivative of displacement is defined as epsilon as dou U by dou X. Velocity is change in displacement with respect to time, dou U by dou T, and the stress field is defined over the domain B over the total time step 0 comma T. Now, the domain is having boundary dou B, and this boundary is split into two parts. One is the Dirichlet boundary, another is Neumann boundary. Dirichlet boundary which is denoted as dou U B, where displacement boundary conditions are prescribed, and Neumann boundary where force boundary conditions are prescribed, dou sigma of B, and one can prescribe values of displacements in the Dirichlet boundary over the essential boundary conditions or displacement boundary conditions are prescribed. So, which is denoted by U is equal to U bar, and then we are going to prescribe force boundary conditions by prescribing sigma is equal to sigma bar on dou sigma B. One can prescribe B bar on B bar the initial conditions U of x comma 0 at time t is equal to 0 is U naught, and V of x comma 0 is equal to V naught, and there is compatibility at time t is equal to 0 on the boundary. So, U naught is nothing but U bar and V naught is nothing but dou U bar by dou t at t is equal to 0. Now, the domain is subjected to also body forces. The body forces are denoted by small b, and this whole body is satisfying the balance of linear momentum, which is denoted by divergence of sigma plus rho times body force is equal to the inertia force, which is denoted as rho times dou V by dou T, where rho is the mass density. Now, so this defines the initial the boundary value problem, and it is together with the boundary conditions and initial conditions defines the initial boundary value problem once we are able to prescribe sigma of x comma t. Now, for a linear elastic case, the stress is related to strain through the constitutive relationship, which is followed by a Hooke's law. So, sigma of x comma t is equal to E times epsilon of x comma t. For an elastic plastic rate independent case, stress is defined locally at each point by an incremental rate form. So, sigma dot is equal to epsilon dot times E if it is elastic, and if it is elastic plastic, then it is defined by E plus E times k plus h by E plus k plus h times epsilon dot if the yield condition is satisfied and f is equal to 0 and f dot is equal to 0 at that material point which belongs to that domain. The stress rate depends on loading unloading conditions and the yield constraint, that depending on if it is a plastic loading process, depending on the criteria satisfied for yield, and if the plastic deformation has started, then based on that the stress rate is defined as either E times epsilon dot or E times k plus h by E plus k plus h times epsilon dot. Now, following a weak form approach, one can define the initial boundary value problem in a numerical setting. So, the weak form approach is widely used in a finite element method. So, the original governing equation that we have, this represents how the domain is behaving under the influence of the external loads and how the body is deforming. So, this governing differential equation allows us to define in an approximate methods what is the residual that is coming. So, the original differential equation is divergence of sigma plus body force is equal to 0. Now, when we make suitable approximations in an approximate method, so to seek approximate solution, and when this approximate solution is substituted in the original governing equation, we will get residuals, and these residuals are coming because we do not know the exact solution. An exact solution is one which satisfies this governing differential equation. So, we seek approximate solution in an acceptable sense that that the weighted residual form. So, this is the acceptable sense in which we are seeking the approximate solution, and this acceptable sense allows us to define the or identify the approximate solution, which is written as some coefficient times some basis functions, where the coefficients are unknown coefficients, and whereas the bases are the known basis terms, and the bases are usually polynomial bases. So, following a weak form approach or a weighted residual approach. So, this is called as weighted residual approach, which allows us to convert the original differential equation into a set of linear algebraic equations, in terms of unknown coefficients or Ci, and in terms of the force Fi. So, these unknown coefficients in FEM are going to be the nodal displacements, and which become the unknown coefficients of approximation. So, one can find out Ki times Ui is equal to Fi for a particular element. So, Kij times Ui is equal to Fi. So, this is the linear. So, the original differential equation is now converted into a set of linear algebraic equations, solving which we can find out what are the unknown coefficients of approximation. So, the weighted residual approach is also called as the weak form approach, which allows us to define approximations whose continuity requirements are one order less than the original differential equation. So, the original differential equation is called as the strong form, and the weighted residual approach, or which is called as the Galerkin approach, when we have the same weights as that of the approximation, is going to give us what is called as the weak form approach, and this weak form approach allows us to have lower order continuity requirements on the approximation function, and that is what is adopted to get the solution. So, the displacement at any time is denoted as u comma t, and the space of those functions is denoted as s of t. Similarly, the weighting function or the test functions are denoted by eta. So, eta is called as the weight function, and u is called as the trial function. So, in a weighted residual approach, you have the weight or weight function, and then you have the trial function, which is used to approximate the governing differential equation. So, here when we substitute in our governing equation, then we get we want to find solutions such that the weak form equilibrium is satisfied. So, integral over the domain rho dou v by dou t eta dx plus g of sigma comma eta must be equal to 0, where g of sigma comma eta is nothing but sigma eta dash dx minus rho b eta dx minus sigma eta defined on the boundaries of the domain, where eta dash is dou eta by dou x. So, this is the weak form that we have got by writing the weighted residual form. Now, one can find out what is the mechanical work identity setting. So, the weak form of momentum balance is independent of the constitutive equations. Now, we assume a time independent essential boundary conditions. So, u bar dot is equal to 0 on the Dirichlet boundary. For any time step t belonging to 0 comma t, the velocity field can be defined to be belonging to the admissible set of functions and can be chosen as an admissible test function. So, eta is equal to v. So, and using the identity dou v by dou t dot v of t is dou by dou t of half rho v of t whole square leads to mechanical work identity that the internal work is equal to the external work. So, we get d by dt of t of v plus rho p internal sigma comma v is equal to p external of v for all the t belonging to 0 comma t, where t of v is defined as the kinetic energy, which is 1/2 integral over domain rho v square dx must be greater than equal to 0. So, which is the kinetic energy. P internal is the internal energy that is stored inside the body, which is called as the strain energy, or is called stress power. So, sigma times sigma double contraction dou v by dou x times dx. Then we have the external power, which is the work done by the external forces or by the body force. So, integral over domain rho b dot v dx plus sigma bar dot v defined on the boundaries dou sigma b. So, internal work is equal to the external work and is independent of the constitutive equations, how they are going to be defined. Now, one can define dissipation and internal or external energy. Now, let us consider the one dimensional model of a linear isotropic hardening plasticity model under dead loading, time independent, B and sigma bar. So, the elastic strain is defined as dou u by dou x minus epsilon p. So, epsilon E is equal to dou u by dou x minus epsilon p, total strain minus plastic strain. The internal energy is defined in terms of epsilon E and alpha for isotropic hardening plasticity as 1/2 E epsilon E whole square, because this is sigma times epsilon E, half sigma epsilon E. So, sigma is written as E epsilon E. So, half E epsilon E square plus half k alpha square dx must be greater than equal to 0, where k is the isotropic hardening modulus, E is the elastic modulus. So, the internal energy must be greater than equal to 0. The external work done by the loads, which is also called the potential energy of loading, which is denoted as V external U, is given by a minus integral over the domain rho bu, which is the work done by the body forces, minus the work done by the tractive force or prescribed forces as sigma bar u defined on dou sigma b, and work done by the applied forces is d by dt V external of u is equal to minus P external of V, where V internal measures stored elastic energy, V external is the potential of the applied forces. Now, let us define the mechanical dissipation. So, the mechanical dissipation is defined as d mechanical is defined as P internal minus P internal of sigma comma V minus d by dt of V internal of epsilon E comma alpha must be greater than equal to 0. For an elastic material, sigma is equal to dou u E times dou u by dou x, where dou u by dou x is defined as the elastic strain, and d by dt of V internal of epsilon is denoted as modulus of elasticity E times epsilon times dou epsilon by dou t times dx, which is simply denoted as integral over the domain sigma dou V by dou x times dx is equal to P internal of sigma comma V. Hence, d mech is equal to 0. The mechanical dissipation is 0 for a purely elastic response, when sigma is equal to E times of epsilon E. Now, elastic plastic case with isotropic hardening, sigma is defined as E times dou u by dou x minus epsilon p, epsilon dot is dou v by dou x. So, the mechanical dissipation in this case becomes sigma times epsilon dot p minus k alpha times alpha dot integral over domain dx. So, now following the flow rule and hardening rule, epsilon dot p can be replaced by gamma times sine of sigma, and so we can write gamma is the slip rate, sigma minus k alpha minus sigma y plus sigma y dx. So, this can be written as gamma f of sigma comma alpha, where f of sigma comma alpha is the yield function, plus gamma times sigma y times dx, where gamma is the plastic multiplier or the slip rate is greater than or equal to 0 during a plastic process. Gamma f of sigma comma alpha is equal to 0, and d mech is defined as integral over domain gamma sigma y times df must be greater than or equal to 0. The plastic flow produces strictly non-negative dissipation. So, there is going to be a dissipation which is always great d mech, which is greater than or equal to 0 during a plastic process. So, a priori energy decay estimate can be made based on the energy function, right. The previous defined inequality as a basic principle is valid for constitutive models under consideration, and we define the energy functional as L of u comma v comma epsilon e comma alpha, which is defined as V external plus V internal, V external being a function of u, V internal epsilon e comma alpha, and the T is the work done due to the forces as T of V. Now, it sums the T as a function of V, which is denoting the kinetic energy, and this is denoting the potential energy and internal energy of the system. So, to compute its rate of change, we use the mechanical work identity, that internal work is equal to external work, and the time derivative of the functional satisfies d by dt is equal of L is nothing but d by dt of T of V plus V external of u plus d by dt of V internal. Now, using the mechanical work identity, we obtain d by dt of L is equal to minus P internal plus d by dt of V internal. So, according to mechanical dissipation, this d by dt of L, the functional L, is equal to minus of the dissipation d mechanical dissipation, d mechanical must be less than or equal to 0. Hence, L is a non increasing function along the solution of the initial boundary value problem. Now, uniqueness of the solution to the boundary value problem. Let us consider the case of isotropic hardening with isotropic hardening modulus k greater than 0. Let u, v, epsilon p and alpha and u tilde, v tilde, epsilon tilde, p and alpha tilde be two sets of solutions of the initial boundary value problem corresponding to the same initial data u naught comma v naught and the boundary data b u bar and sigma bar. Now, to prove the uniqueness, it suffices to show that the two solutions coincide. So, first we observe that T of V minus V bar plus V internal epsilon E minus epsilon bar must be greater than or equal to 0. The internal, since elastic modulus and the isotropic hardening modulus are greater than 0, the kinetic energy and the internal energy net energy is greater than or equal to 0 for this any change in these two sets of solutions between V minus V bar and epsilon E minus V minus V tilde and epsilon E minus epsilon tilde E. Now, the rate of change of the quadratic form we can compute as d by dt T of V minus V tilde plus V internal of epsilon E minus epsilon tilde E. Now, when we subtract forcing terms, we obtain by adding and subtracting the forcing terms, we can write this expression in terms of the yield function and the change in yield function with respect to sigma and change in yield function with respect to alpha as gamma tilde times sigma minus sigma tilde dou f by dou sigma of sigma tilde comma alpha tilde plus alpha minus alpha tilde of dou f by dou alpha sigma tilde comma alpha tilde plus gamma times sigma tilde minus sigma dou f by dou sigma of sigma comma alpha plus alpha tilde minus alpha dou f by dou alpha of sigma comma alpha. Essentially, we are adding and subtracting the terms. We expand on this d by dt, the rate of change in quadratic form. Now, the weak forms of both solutions are going to vanish because V and V tilde are going to belong to the same set of admissible spaces V. So, since the yield function is convex and using the convexity property that we discussed earlier, we obtain that d by dt of T of V minus V tilde plus V internal of epsilon E minus epsilon tilde E must be less than or equal to integral over the domain gamma tilde times f of sigma comma alpha plus gamma times f of sigma tilde comma alpha tilde. So, from Kuntakar conditions, gamma must be greater than or equal to 0, f of sigma must be less than or equal to 0. Similarly, gamma tilde must be greater than or equal to 0 and f of sigma tilde comma alpha tilde must be less than or equal to 0. Integrating in time and using identical initial data will yield that T plus V internal must be equal to 0. Since the modulus of elasticity and isotropic hardening modulus are greater than 0, then we consequently get that U must be equal to U tilde. So, that means when we consider two solutions corresponding to two initial data, then repeating the uniqueness and following the quadratic form of positive definiteness and integrating in time is going to give us a different solution. So, based on what is the error in the initial data, so the error in initial data decreases in time, thus elastoplastic boundary value problem is contractive in energy norm. So, we are going to reach to the actual solution, the less is the error in the initial data. So, this can be shown by considering two different sets of initial data. So, let us look at a numerical solution for the initial boundary value problem. Now, when we can discretize the time into a number of time steps, n is equal to 1 to capital N. For any typical time step, the closed interval is between Tn and Tn plus 1. Now, we replace the time derivatives in the weak form by suitable algorithmic approximations leading to global time stepping scheme, and we restrict the attention to a particular point x belonging to the domain, typically a quadrature point or a Gauss quadrature point that is used for numerical integration. At any time Tn regarding the incremental displacements, we can write delta un plus 1 of x is defined as un plus 1 of x minus un of x. Now, we can show time update and constitutive dependence. So, at any time step Tn, the state of the quantities at any material point x belonging to the domain is defined by epsilon n of x, sigma n of x, epsilon np which is the plastic strain, and alpha n which is the isotropic hardening variable is given and assumed to be. So, these are the equilibrium values that are considered at that particular point. Now, we want to update the state variables at the same point to new values, namely epsilon n plus 1 x, sigma n plus 1 x, epsilon n plus 1 p, and alpha n plus 1. That means, we are incrementing in time step, it is a strain driven problem, strains are increased and we want to find out the other quantities, namely the stresses, the plastic strain, and the isotropic hardening variable. So, the step I depends crucially on the chosen constitutive model and constitutes the central objective of the formulation. In what follows, the attention is restricted to quasi-static problem obtained by neglecting inertia forces. Now, we follow a spatial discretization of the domain into number of small elements in one dimension. A typical element is denoted by BE, and the given stress field sigma n plus 1 of x, we evaluate the weak form g of sigma n comma n plus 1 comma eta, where eta is the test function, restricted to the element domain. Now, we assemble all the contributions of the elements and check whether g of sigma n plus 1 comma eta is equal to 0, whether the system is in equilibrium under un plus 1 and sigma n plus 1. If it is not satisfied, we determine a correction to the displacement field and return to the step I to update what is the updated value of epsilon n plus 1, sigma n plus 1, epsilon n plus 1 p, and alpha n plus 1. So, let x belongs to any point b bar be a given material point obeying a rate independent constitutive model of elastic plastic case. Let us assume that at a local state of time step Tn, we have all quantities described, namely epsilon n p, and alpha n is already known. So, we can write sigma n of x is E times epsilon n of x minus epsilon n p of x. Now, for a mixed hardening case, the additional internal variable q n must also be included in the above expression. So, given a total strain increment delta epsilon x, the objective is to update the basic variable set of variables that we have in time, that is from when we go from Tn to Tn plus 1, which is defined as Tn plus 1 is equal to Tn plus delta t, in a manner that is consistent with the constitutive model that we have discussed earlier. So, this is called as the elastic plastic update over the time interval Tn to Tn plus 1 is treated as a strain driven process with this epsilon is equal to dou u by dou x as the basic independent variable. So, we are going from Tn to Tn plus 1. So, Tn plus 1 is equal to Tn plus delta Tn, and epsilon n plus 1 is equal to epsilon n plus delta epsilon n. So, knowing these two quantities in a strain driven problem and knowing the value of delta epsilon n of x, we want to update quantities, namely epsilon nx, epsilon np, alpha n and sigma n to get the new values, namely epsilon n plus 1, epsilon n plus 1 p and alpha n plus 1 of x. This procedure of getting an update from one step to the other step in a strain driven process is called as the elastoplastic update, is called as the return mapping algorithm. So, what goes into this return mapping algorithm? We see a classical family of scheme for ordinary differential equations. Let f be a smooth function and let us consider x dot of t is f of x comma x of t, where t belongs to 0 comma t and x of 0 is equal to x n is the initial point. Now, one can use time integration scheme of the form x n plus 1 is equal to x n plus delta t for f of x n plus v, and so x n plus v is equal to v of x n plus 1 plus 1 minus v of x n. You can follow a linear interpolation, and where v belongs to 0 comma 1, and x n plus v is approximated as the value of x evaluated at t n plus 1, where t n plus 1 is denoted as t n plus delta t. So, various choices of v will determine what will be the type of numerical integration scheme that we are adopting. So, for v is equal to 0, it is called as the forward Euler scheme, and when v is equal to 1/2, it is called the midpoint rule, and when v is equal to 1, it is called as the backward Euler scheme. And second order accuracy is obtained for a midpoint rule when we have v is equal to half. And this type of time marching has unconditional stability or linearized stability if we have the value of v in this expression which is greater than or equal to half. So, it essentially meaning that if we have x n plus 1/2 is equal to v x n plus 1 plus 1 minus v is taken as 1/2 times of x n, where v is taken as half. So, then we will have unconditional stability when value of v is greater than or equal to half. So, constrained evolution in plasticity. In contrast to standard ordinary differential equations, plastic evolution is constrained. The flow curve is depending upon what is the time step t, which belongs to real number space, and it is going to be defined by the stress state, which depends upon t and extent of hardening variable alpha of t, and both of these belongs to the elastic range E of sigma and is constrained to lie in the closure of the elastic domain. So, we have the elastic domain defined between minus sigma y and plus sigma y, and the boundaries are given by dou E sigma, and this is interior is given by interior of E of sigma, and this whole region together is called E of sigma, which is defined as union of dou E sigma union of interior of E of sigma. So, that together is going to give you the E of sigma, and our sigma of t and alpha of t are defined inside this region, and we want to constrain it within this elastic range that we are having. Similar thing can be defined in the strain space if we are defining in terms of epsilon of t, epsilon p and alpha of t, which belongs to E of epsilon. So, either it can be a strain driven problem defined in stress space or a stress driven problem defined in the strain space. So, the constraint condition is the essential feature that characterizes the plasticity. So, let us consider the incremental problem with V equal to 1 that corresponds to the backward Euler method leading to classical return mapping algorithms. So, plastic strain and hardening variables can be updated by using this backward Euler method. We can write epsilon n plus 1 of p is equal to epsilon n p plus delta gamma sine of sigma n plus 1, and alpha n plus 1 is equal to alpha n plus delta gamma, where delta gamma is given by gamma n plus 1 times of delta t, which is greater than equal to 0 is the discrete plastic multiplier. The stress strain relationship and total strain update is given as follows. We are having epsilon n plus 1 defined as epsilon n plus delta epsilon n, and using the trial elastic step we can write sigma n plus 1 is equal to E times epsilon n plus 1 minus epsilon n plus 1 p. Now, discrete Kuhn-Tucker conditions can be written in terms of quantities sigma n plus 1 and alpha n plus 1, as Fn plus 1 is defined as sigma n plus 1 minus sigma y plus k times alpha n plus 1 must be less than equal to 0, delta gamma must be greater than equal to 0, delta gamma Fn plus 1 must be equal to 0. The backward Euler scheme transforms the evolution problem into a discrete constraint algebraic problem for epsilon n plus 1 p comma alpha n plus 1. Now, the trial state is an auxiliary state which is obtained by freezing the plastic flow. So, you are going to consider no plastic deformation to happen, and is defined as a purely elastic step. The trial step that we are going to follow in the return mapping algorithm is called as the trial elastic state, and which does not in general correspond to a physically admissible state. So, we are going to consider the previous values, equilibrated values of the plastic strain. So, that is why we write from the total strain we are removing the plastic strain to get the elastic strain. So, this is the current step total strain epsilon n plus 1 minus epsilon n p, the plastic strain from the previous step. So, this can be written as sigma n plus E times delta epsilon n, and epsilon n plus 1 p trial is taken as the previous converged value epsilon n p, and alpha n plus 1 trial is taken as alpha n, the previous value alpha n. So, Fn plus 1 is trial is nothing but sigma n plus 1 trial minus sigma y plus k times of alpha n. The trial state is uniquely determined by using epsilon n p and alpha n and the strain increment delta epsilon n. So, we are having epsilon n plus 1 trial is equal to epsilon n plus delta epsilon n. So, that is going to be the trial elastic step, and knowing the value of delta epsilon n one can find out and knowing the previous epsilon n, and one can know the previous converged value which is epsilon n p and alpha n which are nth step values. One can find out what is the trial elastic step by freezing the plastic process during the current step. So, after computing the trial state, once we know the yield function value Fn plus 1 trial, we need to check if Fn plus 1 trial is less than or equal to 0. If this trial state is admissible and stress state is elastic state and as an admissible stress state, then we say that the plastic variables remain unchanged. So, epsilon, the assumption that we made at the beginning of the step is correct, and epsilon n plus 1 p is equal to epsilon n p and alpha n plus 1 is equal to alpha n. The stress equals the trial stress. So, sigma n plus 1 is equal to sigma n plus 1 trial, and the flow rule and hardening law are satisfied, and delta gamma is equal to 0, and the elastic state is a trial elastic state. So, this is how it is that during a plastic process, when we are on the plastic loading curve and we are at a point here, this is sigma n, corresponding value is going to be epsilon n, and we are giving a trial. So, epsilon n plus delta epsilon n is going to be epsilon n plus 1. So, that is what we are giving here, delta epsilon n. So, to get epsilon n plus 1, if this epsilon n plus 1 is resulting in sigma n plus 1, then sigma n plus 1 is equal to sigma n plus 1 trial if it is an elastic process, and at point C the values are alpha n, epsilon n p, and we are having sigma n and epsilon n are the values that are there at C. the same values are going to continue. So, epsilon NP is going to remain the same, and it is an incremental elastic step. That is why sigma n plus 1 will become equal to sigma n plus 1 trial when we are moving from point C, when we are doing an elastic unloading and we are coming to a point C1, and if it is in this case the trial elastic step is same as the final values obtained at the end of step, because the step is a elastic unloading step. Now, so if Fn plus 1 trial is greater than 0, then the trial state is inadmissible. The trial stress violates the constraint condition that f of sigma n plus 1 trial comma alpha n must be greater than 0. That means, if we have this is the admissible stress state is between minus sigma y and plus sigma y. If we are moving from a point inside the domain to outside the domain, at this point if it is epsilon n, and at this point it is epsilon n plus 1 trial, and the corresponding stress is sigma n plus 1 trial. In this case, f of sigma n plus 1 trial, which will be f n plus 1 trial, is going to be greater than 0, because it is outside the yield surface, and such stress state f of sigma greater than 0 is inadmissible stress state, and therefore it requires a correction, and the plastic correction is required, and the Kuntaker conditions imply that delta gamma is greater than 0. There is going to be delta gamma times Fn plus 1 must be equal to 0, or Fn plus 1 must be equal to 0. So, the increment is therefore incrementally plastic. So, during a plastic process we are having either a plastic loading when we move from one point to another point, or we are moving from C to C1 or C to C2 when you have delta gamma is greater than 0, and in next case delta gamma is equal to 0 if it is an elastic unloading or an elastic step, or if it is a plastic step then delta gamma is greater than 0 when we have an elastic plastic process like this. So, Fn plus 1 trial is less than equal to 0 if it is an elastic step and delta gamma is equal to 0, or Fn plus 1 trial is greater than 0 if it is a plastic step and delta gamma is greater than 0. So, essentially during a plastic process, when you are on the plastic loading curve AB, so we are let us say at a point C, and we want to move to another point C1 along the plastic loading curve AB. So, we have taken an increment from point C where it is epsilon n, and we are giving an increment delta epsilon n to get epsilon n plus 1. So, epsilon n plus 1 is equal to epsilon n plus delta epsilon n. Now, similarly sigma n will change from sigma n plus delta sigma n. So, this will result in delta sigma n. So, the point is going to go outside, let us call this C1 dash is outside the loading curve AB, and it will result in sigma n plus 1 trial, which is an elastic trial step, and this elastic trial step is going to cause an inadmissible state of stress, and it has to be brought back onto the yield surface to get the actual value sigma n plus 1. So, the trial state violates the constraint condition that plastic deformation has to always happen on yield surface, and f must be less than or equal to 0 and not greater than 0. So, thereby requiring a correction during the plastic loading process, which results in gamma must be greater than 0, and to achieve sigma n plus 1 is not equal to sigma n plus 1 trial. So, there is need of correction, because sigma n plus 1 is not same as sigma n plus 1 trial. The yield surface also has to expand from E sigma to E sigma n plus 1, and the stress state also has to be brought back onto the yield surface. So, incremental plastic step is characterized by Fn plus 1 trial is greater than equal to 0. This implies that we should have f of sigma n plus 1 comma alpha n plus 1 must be equal to 0 for a plastic multiplier delta gamma must be greater than 0. So, here our objective is to find out what is the values of epsilon n plus 1 p, alpha n plus 1, sigma n plus 1 and delta gamma, such that we are having f of sigma n plus 1 comma alpha n plus 1 equal to 0. The stress expressed in terms of trial state. So, we can write sigma n plus 1 is equal to E times epsilon n plus 1 minus epsilon n plus 1 p, and this can be written as sigma n plus 1 trial minus E delta gamma times sine of sigma n plus 1. So, this is the plastic correction that one needs to find out to bring the stress state back onto the yield surface. So, sigma n plus 1 minus trial minus E delta gamma sine of sigma n plus 1. Now, for delta gamma greater than equal to 0, the incremental problem is written as sigma n plus 1 is equal to sigma n plus 1 trial minus E delta gamma sine of sigma n plus 1, and epsilon n plus 1 p is equal to epsilon n plus delta gamma sine of sigma n plus 1, and alpha n plus 1 is equal to alpha n plus delta gamma, and Fn plus 1 is equal to sigma n minus n plus 1 minus sigma y plus k alpha n plus 1 equal to 0. So, this is a set of nonlinear equations that we have. The only unknown here is the delta gamma, which once found can allow us to define what is the correction to the trial state we need to apply. And here multiplying the stress equation by sine of sigma n plus 1, we can show that sine of sigma n plus 1 is equal to sine of sigma n plus 1 trial, and sigma n plus 1 trial is equal to sigma n plus 1 plus E delta gamma. And using the yield condition Fn plus 1 is equal to 0 and following the consistency condition, we get delta gamma is equal to Fn plus 1 trial divided by E plus k. This must be greater than 0. So, knowing the value of delta gamma, finally we get what is the update. So, we have obtained what is the direction in which we have to proceed. So, we know the value of delta gamma and we have to proceed in the direction of trial elastic step. So, sine of sigma n plus 1 trial, and knowing delta gamma we can find out what is sigma n plus 1, epsilon n plus 1 p and alpha n plus 1. So, from the stress update one can get an alternative representation for writing the stress. So, we can write sigma n plus 1 is equal to 1 minus delta gamma E divided by sigma n plus 1 trial times sigma n plus 1 trial. So, there is a correction factor to the trial elastic state, and that correction factor allows us to find what is the value of sigma n plus 1, and since Fn plus 1 is equal to 0. So, this is as good as the final stress state is projected onto the yield surface, and the stress correction scales the trial stress radially back to admissible value. So, when we are outside the yield surface, we are bringing back the stress state onto the yield surface. So, one can write this for 1D isotropic hardening case in an algorithmic fashion. So, for any point in the domain, define a stress update, the strain update in this fashion: epsilon n plus 1 is equal to epsilon n plus delta epsilon n. We know from previous step what is the values of epsilon n p and alpha n. The time step t n plus delta t n will give you the t n plus 1, and we can find out what is the trial elastic state, what is the trial yield function, and we check whether the Fn plus 1 trial is less than equal to 0. If it is less than equal to 0, then the trial elastic step quantities are same as the actual quantities. So, the next step n plus 1 value is same as the trial elastic step, and this is the stress state is inside the admissible stress state and is satisfying the constraint condition. But if Fn plus 1 trial is greater than 0, then we need to find out the correction factor delta gamma, which is Fn plus 1 trial by E plus k, which is greater than 0, and from which we can find out what is the value of sigma n plus 1, what is the value of epsilon n plus 1 p, and what is the value of alpha n plus 1. Now, so essentially what we are doing is that when we are moving from a trial state by taking epsilon n time plus delta epsilon n will give you epsilon n plus p. The stress is moving from sigma n to sigma n plus 1 trial, and by following a return mapping procedure we are bringing the stress state back onto the yield surface to define what is the correct value of sigma n plus 1. So, the final stress is obtained by returning the trial stress to the yield surface through a scaling factor, hence the name return mapping that is used to get the correct admissible stress state when we are doing a strain driven problem. So, one can define a discrete variational formulation to this convex optimization problem. So, the return mapping algorithm that we have discussed admits a variational interpretation. It is equivalent to the Kuhn-Tucker optimality conditions of a convex optimization problem. So, the discrete problem represents the incremental counterpart of the principle of maximum plastic dissipation. The increment update is formulated as a constraint convex minimization problem. So, the closure of an elastic domain is given by E of sigma, which is defined in terms of sigma comma alpha, such that f of sigma comma alpha must be less than equal to 0, and it is a convex space, right. The functional sigma comma is depending on sigma comma alpha, and that functional is defined as chi of sigma comma alpha, which is defined in terms of trial state and in terms of the trial values of the hardening function, and chi of sigma comma alpha represents a convex complementary energy between the trial state and sigma comma alpha, the actual state. The incremental problem can be then stated as find the values of sigma n plus 1 comma alpha n plus 1 which belongs to this admissible stress state, such that this functional based on complementary energy functional is resulting in any minimum value of chi of sigma comma alpha for any sigma comma alpha belonging to the admissible stress state. Since E is greater than 0, by assumption k is also greater than 0, the function complementary energy function or the functional chi of sigma comma alpha is convex. So, the convex constraint associated with the minimization problem is defined as the f of sigma comma alpha must be less than equal to 0. So, the known data in the current step is sigma n plus 1 trial comma alpha n, with the assumption that f of sigma n plus 1 trial comma alpha n must be greater than 0. So, essentially this is the functional chi, which is the complementary energy functional. So, once we know the trial state, knowing the trial state, we want to get a projection of the trial state to get the correct values of sigma n plus 1 comma alpha n plus 1, which are defined in the admissible stress state, which is E of sigma, and thereby one can write the convex minimization problem in terms of complementary energy chi, which is a function of sigma and alpha. Sigma is the stress state, alpha is the isotropic hardening variable, and you want to get that projection in a manner that this distance is a minimum and that point lies in the admissible stress space. So, that so the return mapping algorithm can be looked upon as a constraint convex minimization problem. So, one can look at it as a closest point projection technique. So, to characterize the solution of the incremental minimization problem, one can introduce an Lagrangian of this form defined as L, or which is a function of sigma, alpha and delta gamma, defined as chi of sigma comma alpha plus delta gamma f of sigma comma alpha, where delta gamma is the plastic multiplier increment and f of sigma comma alpha is the yield function, and chi of sigma comma alpha is the complementary energy function. Now, sigma plus n plus 1 and alpha n plus 1 are the new values and is a minimizer. The first order optimization condition requires that the change in this Lagrangian with respect to sigma and with respect to alpha must be equal to 0. So, dou by dou sigma of L must be equal to 0 and dou by dou alpha of L must be equal to 0, and these are complemented by the loading unloading conditions which decide that it is happening during a plastic process. So, delta gamma must be greater than equal to 0 and f of sigma n plus 1 comma alpha n plus 1 must be less than or equal to 0, and that the stress state is always lying on the yield surface. So, it is the persistency or consistency condition which says that delta gamma f of sigma n plus 1 comma alpha n plus 1 equal to 0. Now, since dou f by dou sigma is equal to sine of sigma, the stationarity condition will result in sigma n plus 1 is equal to sigma n plus 1 trial minus E delta gamma sine of sigma n plus 1, and alpha n plus 1 is equal to alpha n plus delta gamma. So, these equations that we see from a closest point projection interpretation are coinciding with the return mapping algorithm that we discussed earlier. So, the solutions that we is characterized as the closest point projection of the trial elastic state onto the yield surface. So, one can say that the return mapping solutions which we are going to get of the sigma n plus 1 comma alpha n plus 1 are the closest point projections of the trial elastic state sigma n plus 1 trial comma alpha n plus onto the yield surface, which is defined as f of sigma comma alpha equal to 0 measured in the complementary energy chi of sigma comma alpha. So, this interpretation provides a convex minimization framework for the elastic plastic update that we are seeking during a elastic plastic process. Now, when we have combined isotropic and kinematic hardening, one can define the trial state in rate independent plasticity with combined isotropic hardening and in the following fashion. We define an auxiliary variable which is defined as effective stress or relative stress, which is defined as the actual stress state minus the back stress, where the back stress can be obtained from Ziegler's rule, where Q corresponds to the kinematic hardening variable. And for the trial state, we are going to freeze the plastic flow. So, when we freeze the plastic flow and we consider a trial elastic step, the trial elastic step we can define what is sigma n plus 1 trial, and it is given by E times epsilon n plus 1 minus epsilon n p. So, this is obtained from the previous step. So, which can be written as sigma n plus 1 plus E times delta epsilon n, and the auxiliary variable or the relative stress can be defined as psi n plus 1 trial is defined as sigma n plus 1 trial minus q n. Again, here the plastic process is frozen during the trial elastic step. Therefore, the q value, the backstress value is taken from the previous converged equilibrium value, which is taken as q n, just like how we have taken epsilon n p, here we take it as q n, and epsilon n plus 1 p trial is taken as is defined as epsilon n p, and alpha n plus 1 trial is taken as alpha n, and q n plus 1 trial is taken as q n, and the trial yield function is defined as f n plus 1 trial is defined as xi n plus 1 trial minus sigma y plus k times of alpha n. Now, the character of the increment is determined by either f n plus 1 trial is less than equal to 0, then it is an elastic step when delta gamma is equal to 0. When f n plus 1 trial is greater than 0, then it is a plastic step when delta gamma is greater than 0. If the step is elastic, the trial state is the exact solution of the incremental problem. If the step is plastic, a closed form plastic correction must be applied. So, for a discrete problem, we use an implicit backward Euler discretization of the rate independent plasticity model, which results in a set of nonlinear equations as given below. sigma n plus 1 is equal to sigma n plus 1 trial minus delta gamma E sine of epsilon xi n plus 1, and epsilon n plus 1 p is equal to epsilon n p delta gamma sine of xi n plus 1, and alpha n plus 1 is equal to alpha n plus delta gamma, and q n plus 1 is equal to q n plus delta gamma h sine of xi n plus 1. Subjected to the consistency condition that f n plus 1 is defined to be equal to 0, we say that xi of n plus 1 minus sigma y plus k alpha n plus 1 must be equal to 0. So, the shifted stress is denoted as xi n plus 1 is defined as sigma n plus 1 minus q n plus 1. So, subtracting the evolution equations for sigma n plus 1 and q n plus 1, and we get what is the value of xi n plus 1, and using the definition of xi n plus 1 trial, we can rewrite the above equations and show that xi sin plus 1 is equal to sine of xi n plus 1 is equal to sine of xi n plus 1 trial, and together with the scalar condition that xi n plus 1 trial is equal to xi n plus 1 plus delta gamma E plus h. So, the plastic consistency condition which ensures that the stress state is on the yield surface, we can get f n plus 1 equal to 0. That allows us to find out what is the value of delta gamma for a combined hardening case, which is given by delta gamma is equal to f n plus 1 trial divided by E plus k plus h must be greater than 0, and using this condition then we can write in terms of sine of xi n plus 1 trial, and in terms of delta gamma what is the value, what are the updated values of sigma n plus 1, epsilon n plus 1 p, q n plus 1 and alpha n plus 1. So, in summary, in this presentation we have discussed how to define initial boundary value problem, what is the energy framework during a plastic process, and what is the computational approach that we need to follow, and how we define a time discretization using a backward Euler scheme for a strain driven problem, and how the global equilibrium is enforced, and how elastic predictor plastic corrector technique is used for return mapping for both isotropic hardening and combined hardening cases. In a one dimensional problem we have discussed this approach. Thank you for your attention.